Good afternoon. As always, I am asking you whether you hear me or not. In case you don't hear me, please send me a message. Our last lecture before Easter tries to summarize what we have seen so far about the two research questions which we are investigating. As always, it's not a question of remembering details, but it's a question to understanding the way of thinking. It's a way of thinking. Sustainability, it's a way of thinking. It's a method that tries to compare different options. This lecture, therefore, is going to be reasonably different from the previous ones, because we are going to concentrate on trying to think, to reflect upon our research questions, and to see which are the factors that we need to consider, and which are the difficulties which we find in trying to elucidate these problems, in trying to understand whether it's going to be difficult to find a solution or not, and especially the more aspects of the questions which are coming out during last few years. Because in reality, what we found out is that the research is going on, of course. The research is going on, and you may know that there are some bioplastics which are coming out as compared to petroplastics. We define the petroplastics, the plastics obtained from oil, therefore, which are a competence of the petrochemical industry, which then supplies the material to the plastic industry to fabricate plastic. Supplies the polymer. You need to remember that polymer is not the same as plastics. Plastics is the final material, and the polymer is the core of the material, is the building brick of the material. Then you have some additions of additives of different nature, and you get to plastics. So that's the first question. Bioplastics are sustainable, more sustainable than petroplastics. You are not able to answer yes or no. Well, it depends on the place where you are. It depends on what you are thinking of producing with these bioplastics, which kind of petroplastics you want to substitute, because it might not always be possible to substitute petroplastics with bioplastics. Either because the bioplastics able to substitute the petroplastic is not sufficiently good, their performance are not what you expected. You may, for example, when it's a question of product, when you start using a product A and then you pass to a product B, which might apply to anything, but also to plastics, you may consider, for example, that you buy the milk bottle brand A, and then you find in the supermarket the milk bottle brand B, and you make your comparison. You may say, for example, brand B doesn't produce a milk which is good enough, then as good as the brand A. Then there are other considerations, the price. Some of the bioplastics which I am showing you have costs which are much higher than the petroplastics, which they are supposed to replace. And this is another factor, because sustainability means social sustainability, economical sustainability, and environmental sustainability, which is the one on which we concentrate. So first question is, are we able to replace petroplastic with bioplastics, and then we feel that we are more sustainable? That's the first question. The second question, which is interconnected to the first, is that we have exceedingly amounts of waste, and so we want to understand whether we can use these waste or some part of this waste, for example, agro waste, waste from agricultural production, to produce bioplastics. So bioplastics are plastics produced from biological matter, which as such are biodegradable. So they have some kind of interaction with biological organisms and they tend to degrade. So that's the definition. We need to come out from a naive perspective in the sense biodegradation, is it always good? Well, biodegradation means that the materials are going to have an attack from biological organisms, microorganisms, etc. They might be even edible from materials. There are some materials which you know are attacked by animals. For example, woodworms would eat wood and some parts of wood, cellulosic parts of wood. So this is something we know, and in general terms is not good because it generates a decrease in the properties of the material, and therefore we have tried to avoid this for many, many centuries, I would say. We tried to avoid wood. There are a number of treatments of wood to avoid wood to be attacked by worms, insects, etc. Thinking of railways, railway sleepers were made in wood, and wood was treated in order not to be attacked, in order to not to have accidents because the sleepers are consumed, are worn out. Now the perspective is changed about biodegradability. People are becoming enthusiastic about biodegradability, and because they think that what is more biodegradable, more easily biodegradable, it's better. This might also be the case, but it depends what you want to do. For example, there are some materials which are necessarily single-use materials. And for example, non-washable biomedical items, say some cotton gauze, if instead of cotton gauze we use some biodegradable fiber gauze, which serves the purpose wound healing, so you are able to apply your medication and then you can throw it away and it is biodegradable after being mechanically decomposed, so being chopped down to a small dimension. In this case, biodegradation is important, but in another sense, we don't have many materials which can do like that. Many biomedical materials which are safe and on the other side may decompose easily. Some materials are implantable and in fact they decompose inside your body, which can imply that they won't be, your wounds are healed, but on the other side, the time is controlled. Because there is also a question, biodegradation is also all about time. You want to biodegrade something and you want to control the process, which is not obvious because talking about microorganisms is not easy to control their action. And so to say that in some time they are going to be decomposed. That's what they are trying to do with composting. Composting, well, compost is it's something which is, think of cow dung. Compost is as ancient as the humanity. On the other side, composting is a quite new phenomenon. Composting means that we have a material which we are able to insert into compost and which will act together with compost in the same way that compost does. So creating this kind of fertilizing material which will aid our crops, our cultivation to grow, and our plants to develop. This is not obvious as you have seen. You have seen also with some, you may be embarrassed even in discovering that in reality, the so-called compostable bioplastics are introduced just in a few percent into compost. Even if they are compostable, we are not able to make a compost just made of composted bioplastics. So we cannot just chop, in practical terms, chop a supermarket bag and use it as such, by digging a hole and putting in the field. We can introduce into compost in special implants, etc., in quantities which are limited. Of course, if you discover studies that demonstrate that we overcome this problem, I'm always happy. It's also a question of this course is also a question of looking into literature, looking into data, and try to make sense of them. If the materials are not compostable, there are some rules about composting. The 13432, it's well known, the European norm 1342, concerns times and pH of composting, etc., which gives you the certification of compostable for a material. This is of legal interest because then you are able to sell your bag as compostable, and then you can sell your chopped remainings of your bag to put in the brown bin and to sell everything to your composting plant. In practical term, if the material is not compostable, then it is biodegradable. Please be aware of the fact that anything apart from very hard stones, but for sure any plastic is in very, very long time biodegradable. When you think, I sometimes mention Greta because it explains very well the problem. When you see your small fragments of plastic coming from a bottle at sea, that means that some kind of biodegradation or photodegradation by the sun, the action of the sun, has happened. But this is too slow to be practical. In practical terms, what we find out is fragments, microplastics, on the sand or in fishes and so on. And this creates a lot of concern and so on. Also, we would like something else. We don't just aim for the material to be biodegradable, but we want that the material is mineralized in the end. So there is not volatile organic compounds going around. So in the end, it becomes mineral, which means it becomes inorganic, which means, again, in terms of soil, it is inert. Basically, it behaves like a sand or a gravel, and we can dig a hole and put in soil, and we are rather safe. This is what happens in bacterial degradation of plastics, of some types of plastics, which we investigated last time. There is another question about this, which is a lot discussed a lot during last year. If we are not able to compost plastic, if biodegradation is too slow, maybe we could think of recycling something. This is another scenario which is acceptable even for bioplastics, because if bioplastics are not compostable and their degradation is quite slow, I may think, well, I can melt them. The very precise people wouldn't say melt, would say soften. Why? Because plastic is normally not a crystal. Crystal melts, like ice melts. Plastic do soften, but whatever the case, do soften and become kind of viscous fluid, more similar to mayonnaise and ketchup than to water. You can reprocess it, and you can make plastics, other plastics which are not of the same quality of the previous ones. We are going to discuss it further, but please remember that one of the main chain to our reasoning is one of the main thinkers is thermodynamics, which means that, well, we gave some energy to the material and we have softened it, molten it, but in the end, the quality is lower. If you add the transparent plastics, you lose transparency, which might be a problem, not only from a marketing point of view, also from the point of view of application. Another interesting bit, are we bound? Well, we assume that biodegradability is a good thing. Are we bound to consider biodegradability only biodegradable plastics, only from biological raw materials? Are there other materials which create biodegradable plastics? Well, yes, there are. There are some oil-based plastics which are biodegradable, which creates some study of the fact that any plastic could be biodegradable. As a general, it's a strong statement, but you know, already in the 60s, 60s, in the 70s, they were investigated about naphthalene, and they were worried about the fact, you know, the reason was the opposite one. They were worried about the fact that naphthalene, which was supposed to last because it was a preservative, we still use naphthalene to preserve wool. They were worried about the fact that it was attacked. It was attacked by some kind of worms. It was attacked by some bacteria. This was a quite important discovery. It wasn't, well, from a chemical point of view, it's not a surprise, because if you know a little bit of chemistry, naphthalene is two benzenic rings. It's made of two benzenic rings, and there are lots of biological substances which create polyphenols. When you treat lignin, you usually get polyphenol. Even spent coffee grounds create polyphenol. And therefore, it's not a surprise that this might have some interaction with bacteria. Anyway, from a more commercial point of view, in the last few years, a number of biodegradable plastics not obtained from biological raw materials have been obtained and being marketed, like polycaprolactone, polyester imide, and well, the advantage. What's the advantage of using oil? Well, we consume oil to do that, okay, but we consume oil anyway because we consume a lot of oil as fuel for different kinds of machines and systems. So this wouldn't be a problem. The advantage is that there is just one sector which is in charge of the production of these plastics. The other possibility is that we get rid of all these problems, concerned with cultivation, crops, compostable, not compostable. They are not compostable, these ones, PCL and PEI. PCL has got some importance into design because it tends to soften at low temperature. So it's a kind of waxy bioplastics, well, biodegradable plastics, therefore bioplastic, but it's obtained from oil. Okay, structurally they are similar to traditional petroplastics, but they are biodegradable and not compostable. They wouldn't act quickly enough into your soil, even if you have the right condition of pH, humidity, etc. So let's come back to recycling. So recycle is a good option, maybe. Recycling, it's possible for some types of plastic. Of course, as we were saying, we are talking about thermal recycling mainly. You may remember that recycling has got three streams. You may have mechanical recycling. Mechanical recycling is always present. When you talk about recycling, you start always from a mechanical operation. Please remember. This is essential because the information is very confused also in the media and the newspaper. You always start from a mechanical operation. You may stop there if the material doesn't soften, doesn't melt, which is the case, for example, with wood. With wood, you can make wood flour, wood powder, and in the end, you put your wood powder in another material, for example, or you make chop in larger bits, but again, you make other materials. Or you can burn it, because what doesn't melt, it burns. And what the plastics which degrade at temperature without melting are called thermosetting, because with temperature they become harder and then degraded. They basically become carbon. They might also be set to fire. This is not always the case, but it's always the case that they degrade to carbon. This is the case for some very important and popular resins, like the ones which are used a lot, for example, in DIY, in work from home. You can make, if you want to bond something, also artisans use it a lot, shipbuilding, etc. Room temperature operation. Room temperature operation, it's a plus in work, because heating anything costs money. If you do experiments, I've done lots of work during my life on composites. In universities, usually you do composites with glass fiber, carbon fiber, and thermosetting resins, more than thermoplastic resins, because thermoplastic resins can be thermally recycled, so they melt, but you need an oven. You need a big oven and mold and heated mold to make your operation. Or you need injection molding even. You can make injection. You need to inject your plastic into a mold. So it needs to be viscous, but reasonably viscous. So enough to enter the mold and to be molded in practical terms. So thermosetting cannot, in principle, be replaced by bioplastics which are based on polysaccharides like polylactic acid. Polylactic acid, it's a thermoplastics, and so it is PCL. So it is PHA, polyhydroxyalkanoate, the bacterial plastic, etc. And so are thermoplastic starches as well. There is a possibility to create also some thermosetting without using oil, without using chemicals, and making them with biological raw materials. If you want to have to come down to after having said this great research teams, it's important to consider very low-level considerations, which are very important anyway. The fact that the collection needs to be effective. So if you want to recycle anything, you need one material. You need just that material. That's why recycling of PET, polyethylene terephthalate, which is the material that constitutes most bottles, most water bottles, etc., is reasonably good because it's easy to separate. Of course, there are some other kind of plastics which might be very interesting, also very good. I would mention, for example, the polyether ketone. It's a conductive plastic, which has a temperature of softening around 300 degrees. So it's high application, very good for engineering purpose. The problem is that the market segment of polyether ketone, PET, is less than a few percent. So in the end, you need someone that collects some PEK and recycle it. Otherwise, it wouldn't mix with anything because the other plastics are less noble, say. They melt at lower temperature, they soften at lower temperature, and it's left alone, and it's a polluter. In the end, it pollutes your plastic stream because the less noble plastics are the 99% of plastic that you collect in your bin, and these particular plastics, the plastics which are one of the plastics which are reported in number 7, together with thermosets and special thermoplastics, like also nylon. Yes, you can throw a nylon sock into your plastic bin, but you are going just to pollute your plastic collection because nylon is so little, and nylon for socks is even less. So because it is a special, it is treated with chemicals in order to get this small thickness and so on. Okay, so there is a big question about collection. So recycling might be an option for very popular, say, plastics. There is no reason why PLA wouldn't become a popular plastic. I'm sure it will. If they don't concentrate too much on composting, it might become a very popular plastic because it's used in 3D printing, PLA. So it might become popular, and in the end, we might consider to recycle it, to separate from the other plastic and to recycle it, not just to compost it. So please be aware that the destiny of bioplastic is not compulsory the composting. They might be recycled. There are some difficulties. As you may have heard already, it's not the case that not all petroplastics can be replaced with bioplastics. So in practical terms, the market concentrated on some types of plastics, which in particular terms are the plastics, the most common plastics, the ones which I was mentioning as less noble. Forgive me for this assumption, but they are the less noble. The commodity polymers. So the polyethylene, polypropylene, polyethylene terephthalate, the ones which are in the classification 1 to 6, excluding polyvinyl chloride, which is the oldest one, but it is gradually coming out of the picture because of the pollution created by chlorine in case they are burned, in case they accidentally come into incineration implants, because there is also the case that some plastics are incinerated. PVC would produce some dioxins, etc. So the commodity plastics were the first aim for replacement with bioplastic, or to replace the petroplastics with bioplastic. Are we happy with that? Are we happy to replace? Are we always happy of the quality of petroplastic with bioplastic? Well, in most cases we are, in a number of cases we are not. We are not happy. And what happens? If we are not happy, two big consequences happen. In single use, if you consider a plastic for single use, we should take single use out of the picture. It should disappear, single use, apart from special uses like in the hospital, etc. Hygienic use, I would say, more generally. Apart from that, single-use plastic needs to disappear. Yes. But if we want to replace petroplastic with bioplastics for single use, and bioplastics are not effective, in the end, what happens? Well, more in practice, put it more in plastic. If your supermarket bag in bioplastics is not strong enough, what do? You take another one, or you take two to carry the same amount of food or items. So in the end, you consume more plastics. And more consumption means more waste. So there is a balance, because you can remember that before recycling, there is reuse. If I have my old polyethylene bag and I am able to reuse it for 10 times, say, it is a tenfold sparing of waste. I have waste is reduced by one order of magnitude if it is 10 uses. Also, biodegradation reduces the duration of plastic, reduces the duration of products. So, for example, if I want to make something durable, let's say 3D printing. 3D printing with PLA. 3D printing with PLA, it's interesting because at the beginning we were making just prototypes with PLA. Then a prototype, the prototype is easily destroyed after a while because you just need it to validate your project. You may take a photo of your prototype, but then the prototype goes in the bin, might go in the bin. So PLA was good for that because it was biodegradable, and in any case, you could think of recycling it. It wasn't possibly compostable, the PLA for 3D printing. Now, what's happening with 3D printing? 3D printing is gradually shifting from the pure prototype production to the production of longer duration items. Therefore, we realized that we might need other kind of plastics. So ABS is not very recyclable. It's a thermoplastic, but it's an engineering polymer. As opposite of commodity polymers, there are the engineering polymers, which are ABS, nylon, so polyamide. Polymetal methacrylate is a bit on the border between commodity and engineering polymers. And PEK and others, which are less diffuse. But anyway, BMI, for example, is Malay meat. But apart from this distinction, you can say that life duration is the first characteristic of sustainability. A material, a product that lasts more time is more sustainable because we produce less waste. If we use one car for 20 years or 5 cars for 4 years, it's always 20 years. But the one we use it for 20 years that we repair, well, it's going to pollute more, of course. It depends how much we use it. If we use it a lot, pollution might have a difference, but it's always marginal. In reality, disposing of 5 cars as compared to disposing of 1 car makes a lot of a difference if you think of about 1 ton of different materials. So it's fair to say that the first characteristic for sustainability is life duration. If we are able to make materials and products last more, it is more sustainable. This is particularly true for plastics. For plastics which are not that heavy, so in the end, you can make a lot of a difference if you use 1 or if you use 10. Also in terms of prices, because in terms of in plastics, what we find out that we have a production of millions of pieces per week. If you consider, for example, bags, and you may consider the impact of all that has on the environment. Okay, but we are not happy with bioplastics. We still want original plastic because, well, this is an approach. This is a possible approach. This is a possible approach. I want to have my old polyethylene bag. I can produce it with some biological materials instead of using oil. It's already better because, especially if I don't have oil. For example, Italy doesn't have much oil. It has some oil at sea, in Sicily or even in the Marche region here by Ancona, but it's not that much. It's always been marginal. It has been pushed because of nationalism or autarky views, especially between the 30s and the 50s. But apart from that, it would be nice if we could use to produce plastics other than oil, because we have to buy oil or to buy polymers in the first place. So you may, for example, produce ethanol from sugar cane and then make polyethylene. This has been done. There are a number of options. This is called bio-based plastics. Bio-based plastics tend to resist on the market because in the end they have a small chunk of the market, and they were dismissed a bit when they appeared on the market. People were saying, well, I just want the bioplastic, or if I don't have the bioplastic, I keep the old one. In reality, this changes a bit, because if I have waste from sugar cane, we know that waste comes into the picture. If I have waste from sugar cane, sugar is a huge industry. I have waste from sugar cane, the so-called bagasse, and that kind of molasses or similar stuff, which I don't incorporate in sugar or in sugar products. And so in the end, I may consider making the original, the true polyethylene, which is going to be at the same, roughly the same performance as the old polyethylene, because it's the same polymer. It might have shorter chains, but the performance is going to be about the same. Then there is another question, which is tricky and important. I wasn't able to replace by bioplastics the thermostatic plastics, the resins. Can I do that using biological raw materials? Can I obtain thermosetting resins or plastics by using biological raw materials? Well, there have been a number of attempts. Some are more successful, some are less. In some cases, they are not exactly the same. It's not like polyethylene replaced by ethanol from sugarcane. In that case, you get polyethylene, and that's the performance is about the same. In the case of bioepoxy is not exactly the same, but well, it works. Well, it's not exactly the same. You should also consider that epoxy as cyanacrylate are horrible materials from an environmental point of view, but they are one of the best materials in terms of production of important engineering structures. You can make an aircraft wing in a composite made of carbon fibers and epoxy resin. Well, these are not commodity polymers. These are engineering polymers in the fullest sense. So comparing with epoxy, you can imagine that bioepoxy might have some difficulty, but it works. For less demanding engineering application, it works. And it was obtained from rapeseed. There is another question which I bit skipped, but we have talked about it in the previous lecture. That kind of competition with food. Polylactic acid obtained from cornstarch. Well, okay, but cornstarch, I can eat corn kernels. I can use cornstarch to make preparations. In Italy, we have polenta, which is very popular. Any kind of culture has got some preparations made with starch, cornstarch or similar starch. So using starch to make bioplastics seems a waste and not very ethical as well. That's why waste comes again into the picture. With thermosettings, coming back to thermosettings, they were using some plants which don't provide much food in reality. They are marginal as for in the food sector. Like rapeseed. Rapeseed has got some popularity now, but they came back in the picture. It had some popularity in the 60s that there have been cases of poisoning with great rapeseed oil, and because it contained a very aggressive acid, the elusic acid. But later on, it came back into the picture. But you are not going to serve your food seasoned with rapeseed oil because it's not that good. Castor oil is even worse. Castor oil is a heavily diuretic material, so oil. So you wouldn't use it. But it's good to make polyurethane. Grape seeds, from grape seeds even, which is the waste from the grape industry, we can make, polyester, unsaturated polyester. Because polyesters, you have saturated polyester, which melt, which soften, like PET is a saturated polyester, or insaturated polyester, which in practice cross-linked, are heavily cross-linked. And after you add to them an argon. So these are families of thermosetting materials. In some cases, the ambition is lower. We don't want to replace epoxy. We know that bioepoxy is going to be a step below, normal epoxy. But we want to get rid of bisphenol A, which is used in the preparation of epoxy. the chemical synthesis of a compost. Okay, so we can say that we are not using really something which is in competition with food, which is not bad. Grapeseed oil in the end is not a real market. Also because it belongs to a productive system, the productive system of grapes and wine, which is a huge one, a huge importance. So in the end, we don't care about grapeseed. You don't feed about on the grapeseed oil anyway. So it seems to be good. But on the other side, grapeseed is a good example. But would you plant ricinus, which is the plant from which castor oil comes, to make bio-based plastics? Well, no, or possibly yes. Possibly yes, if there is a competition with something else. If you are already doing biodiesel, you might not have a competition with food, you might have competition with biodiesel. I am already doing biodiesel, so why not trying to make science on bioplastics? That's another story. That's how, in practical terms, olefins like polyethylene and polypropylene were developed. In practice, there was such an excess in production of oil for fuel that it was quite easy to get this kind of monomers and polymerization. Both polypropylene and polyethylene required a long time research to be developed in the fullest sense of. About the question of hemp fibers, cannabis hemp, about the question of hemp fibers. Yes and no, in the sense that Mattia was asking here if we can make bioplastic from hemp. Well, bioplastic from hemp, I need to be clear about that. Bioplastic, you can make bioplastic from hemp waste. It's not all going to be compostable. I've done some experiments myself. The bioplastics which you use for also for 3D printers is PLA loaded with some hemp. I don't know exactly how much hemp there is in there, but it's based on PLA, on polylactic acid. And so it's not pure hemp. Yes, but you can use hemp. The problem with hemp and the problem with anything, with oil, with resinous and whatever, is that you have first to have a production system. With hemp, I am afraid this is not the case yet. Then we could discuss with hemp. I am always with pleasure discussing with hemp. Well, not too much because hemp creates great expectations, and in the end, we weren't able to succeed because the productive system is not yet in place. The problem is also this. If I have to create a plant or to modify a crop just to make bioplastics, it's not worth. If I don't have rapeseed and I just use it to produce bioplastics, it's probably not worth, and not very sustainable as well, because if I have to replace something which is not in which is in the food sector, I mean, if I have to replace say olive oil, olive trees with rapeseed plants, well, that means that in the end I don't have edible oil and I have non-edible, well, slightly used in the food industry as an additive oil. Castor oil is even worse. If I have to plant resinous to replace olive oil, I would have a revolution in a number of places. People wouldn't accept that, and they would cry. On the other side, and that concerns hemp as well, there is the question of remediation. If I have a landfilling site, for example, which has been decommissioned, it has run out of use, or I have been asked by the community or by the European Union or by the government to decommission that landfilling site, I could well plant, why not, resinus? Because there wasn't there in place, there was nothing in place. I could put resinus. They would say, well, probably the place is polluted, and they would ask to me, well, you plant something that is not going to use it for food, isn't it? So I can say, well, yeah, no, it's not used for food. I can use bioplastics, not in the food sector. Bioplastics for making plastic objects of other kinds, for making thermosetting resins, and therefore which might be used in other sectors, in engineering sectors, apart from the food sector. Because, in the food sector, regulations are very strict, rightly so, from the hygienic point of view and from the point of view of release of volatile organic compounds and of heavy metals as well. Coming back to the example of the landfilling, of the decommissioned landfilling site, I would say also that heavy metals are usually actors in there, are usually present in there. And some plants, as hemp, for example, are able to take off of the soil heavy metals. Then I can burn hemp, for example, to produce heating, to produce energy. But in the end, I wouldn't be able to use it in the food sector, in textile sector, if heavy metals have been absorbed by hemp. Oxo-degradable plastics is another option for people which are not happy about the new bioplastics, like PLA. In the US, as I have already mentioned, they are popular. In India, they are popular because there is a hidden assumption, there is a hidden agenda into there. The hidden agenda means something which is not declared but is obvious. That in places like India, they assume that landfilling of plastics at this moment in time cannot be avoided because the amount of plastic landfilled is too much that I cannot impede that. So I can add some additives to this plastics, to this traditional plastics, petroplastics. I could add some additives, and at the end of life, this polypropylene, polyethylene, etc., would decompose. These additives can be of natural origin. There have been a number of studies, for example, in putting in the chain of polyethylene or polypropylene some PLA. I can put some PLA, and in the fullness of time, I will come to a degradation, to a biodegradation. Of course, this doesn't solve Greta's problem, because in the end, I would have microplastics. That's why the European Union never accepted the oxo-degradable plastic. On the other side, I might have some fragments which might be combusted and to serve as fuel for some energy production. Possibly could be recycled if they are, as always, they are collected in the proper way. But in other sense, I wouldn't be sure. I'm talking in this moment, of course, I cannot be sure what will happen in the next few years. But since there has been some deception about some performance of polylactic acid, especially as commodity polymer, and also because some countries have no shortage of oil, so in the end, I think that oxo-degradable plastic will remain to the picture. There are a few products which are additives without even doing some cross-polymerization, like the one I was mentioning before with PE and PLA, but you can just add to your plastics and after some time it will decompose. Of course, this is intended for a limited time of use of plastics, which clashes with the fact that we have to reduce single-use plastics. We don't want single-use plastic bags. We wouldn't want single-use plastic bags. In fact, I am sure that all the discussion about composting will be overcome by the fact that gradually people would like to get rid of single-use supermarket bags. And therefore, we wouldn't need compostability anymore. We would like to have possibly recyclable plastic bags. But of course, if they are dumped on the soil, if they are dumped in cities, like the situation in many countries, and also you need to consider that these countries like India, they have a large number of injection molders. So for them, it's not a problem to produce polyethylene and polypropylene. It would be more of a problem to produce polylactic acid because they would have to buy starch from somewhere else, and then competition with, the competition with food problems, etc. So I think they are still in the picture. As I was saying last time, one option is bacterial degradation, and material degradation happens with any kind of, almost any kind of plastics. But there are some bacterial strains which degrade some definite plastics. There are some cases in which this is known to work. This is known to work, for example, with the Pseudomonas for polystyrene and the tenebrium from expanded polystyrene, therefore also known as styrofoam. Why did they concentrate on polystyrene? Well, there are other plastics. There are also agents which decompose polyethylene and polypropylene, although with not large effectivity. In reality, what happens is that it was the reverse the study which was done on naphthalene in the 60s. The first papers were back in the 60s. They were done a study with naphthalene, and they discovered that the Pseudomonas are bacteria which are very diffuse, and they are at the origin of a number of skin rashes, for example. And so it's just a question, it happened by accident that basically naphthalene was managed, but some, the 60s, the regulations were too relaxed, much more relaxed now. There was probably some work that managed to package polystyrene or styrofoam, and they found out that they were contaminated, and they showed some signs of degradation. Because styrofoam came out as eternal packaging material, and it is quite so. It's quite eternal, even in water and even in seawater. It tends to be quite eternal because water doesn't tend to penetrate. So it is a good idea to reverse the perspective and to say, why not allowing these bacteria to make their work, to encourage their work, and to making them acting as composters for these materials, in making them composting these materials. Well, this is a good perspective. The problem is that passing from a lab scale to an industrial scale, uh, it is not clear what they will do in the soil, if they will create a very good compost. But studies are ongoing, so I'm sure they will come out with the idea that they are able to close the cycle to make compost. Because the idea is that they decompose plastics, they make compost, and then they could recreate other plastics because they they act on food waste, making a compost, and then they feed on that food waste to creating other plastic, as I've shown to you last time. And of course, there is the health concerns because I wouldn't leave Pseudomonas aeruginosa going around for even for even for decomposed plastics. I am not sure that we are able to control that. In lab terms, yes, in lab terms probably we are. But I think that's something to follow for the next few years because this is going to be industrialized, and especially PHA is having a increasing success. Also because there is the possibility to select which kind of bacteria we want to produce the plastic. Kind of bacteria which, for example, are also very good at composting food and are also not harmful for us and or for the animals. Because please remember that where compost is, there are supposedly there are some animals, and therefore we need to be sure that the bacteria we introduce in that context are not harmful for them. So we are not limited to polyhydroxyalkanoate, which started in the 30s, and well, it had a very limited success because the 30s was the time where biodiesel, for example, started. Biodiesel produced, well, we were mentioning hemp oil before. We were mentioning hemp before, and hemp oil was the idea of Ford, of Henry Ford, to be able to replace the diesel obtained from oil distillation. Because, well, Ford's idea was larger than that. He wanted to use hemp, of course, for textiles, which was the original use, and for other commodities, also to put it in cars, for example, in door panels in cars. And he did also a study on which kind of pieces in the car. Almost all the pieces came out with the conviction that almost all the pieces, apart possibly from brakes and wheels, but most of them, and tires, of course, but most pieces in the car could be replaced with hemp. Well, the exception, as I was saying, brakes, wheels, and steering wheel, probably steering wheel, but and of course glasses. But that was interesting in investigation terms. Then the reality went another way because petrol was so cheap that in the end petroplastic were prevalent. But it is good news that there are some bacteria which are even able to develop polylactic acid, because polylactic acid is the most diffuse bioplastics, and the diffusion of 3D printing puts PLA at the forefront because it's easy to manage. It requires a heating which is needs to be less uniform, doesn't require to be as uniform as the one for polyethylene and so on. Well, you could do also 3D printing in polyethylene, but making wires out of polyethylene would be not easy. Wires of that dimension, and so the question of additive manufacturing is still to come. So polylactic acid is at the very forefront with 3D printing. The real competitor is ABS, is acrylonitrile butadiene and styrene. So industrial bioplastics like PLA are really the most interesting product in terms of bioplastics. That's why I don't want you to think that it's going to disappear soon or that it was a failure to introduce polylactic acid. Of course, as I was saying, there is the competition with food, because in practice, well, corn kernel are the food item, which has become over the years, because of monoculture, it has become very cheap. That's why in the end polylactic acid was proposed to be obtained from cornstarch, in reality from sucrose, because they depolymerize cornstarch, because you know the kernels have all different dimensions and different properties, and therefore even in just one corn cob, and in the end they depolymerize to sucrose, which is always the same, and they repolymerize. I've said already the importance in 3D printing. There is waste which could be used instead of making all this process with cornstarch and depolymerizing it, etc. Because remember that polylactic acid is successful, but it was started to be developed in the 20s. Then there was a patent again in 1970, but in reality it just exploded when its consumption, when the being called a monoculture and owned by big companies, in the end by supranational companies. So in the end they had no interest to develop something in a particular area. But what happened is that in the Midwest, in the Green Belt in the US, the so-called corn belt, there was too much corn, it was too cheap, and in the end monoculture had a yield which was lower and lower, and the material became in reality cheaper and cheaper, because they were expanding gradually the amount of soil cultivated, land cultivated with corn. In fact, they introduced soy, and then they tried to make also bioplastic for soy, which is successful as well. And there is also a 3D filament made with soy, because soy is the kind of comrade with the corn that helps corn, because otherwise corn was so filled with pesticides and fertilizers, and they enter into sustainability questions. They enter in the picture in terms of sustainability. There is a minus factor for polylactic acid obtained from corn, and in fact there is also a filament obtained, a 3D filament obtained by soy, the so-called fila soy. Soy helped the corn in maintaining this kind of monoculture and in increasing the yield of the cultivation. Why not using waste? Because we have lots of agro-food waste. There is waste is divided, can be roughly divided in waste which cannot be avoided. Banana peels cannot be avoided. It's a waste that we have anyway if we consume bananas. Other kind of waste can be reprocessed, like skins in apple, skins in lemons, oranges, etc. Reprocessed, and they can be reused in the food industry. Banana peels, they aren't used although they contain a lot of starch, especially if they are green, they contain a lot of starch. So in the end, why not using waste? Yes, we can use waste. You can use waste to make thermoplastic starch. Of course, they are not as controllable as polylactic acid, and in most cases, they are not injection moldable, which means they have different characteristics. They don't soften in the right way to be injected. They might be too viscous, so they might need to be molded even in open mold, closed mold, and so on. But it can work even as an addition, as I was saying, the addition with hemp. The guy in Sicily that has tried this to do this experiment in putting some hemp powder into the PLA filament. He was very clever in doing that because he was able to demonstrate that even with some hemp, so with the wire being stronger, the 3D printer was working anyway with this kind of filament, and it was prepared to the perspective that 3D printing is evolving from prototyping to real engineering of the materials and products. And the advantage is that we have a variety. In using waste, the advantage is that we have a variety of starch material. We have a variety of starch material from a number of cultivations, and even animals produce. There are animals which use their own starch, which is called glycogen. And we could try to not use necessarily something which is edible, even by animal. If it is not edible by us, it's already a mistake to use something which is edible by animals to make bioplastics. And it's a minus for sustainability, because if we produce bioplastics, then we have to buy or to cultivate something else to feed our animals. So it is a balance to be considered. Thermoplastic starch can be, I was mentioning last time that there is also some glycerols from animals, but thermoplastic starches are made from starch with some additives, some plasticizers. The most typical ones are acids, apart from glycerol, sorbitol, xylitol, etc. Some acids which are usually added as well, which are acetic acid and citric acid in particular. I mentioned the last time the lemon and the carbonate. Sorry for what happened last time, last few minutes. But I was mentioning the last slide last time the creation of this new bioplastics, which is very interesting. The carbonate, lemon and carbonate. We know that limonene it's one of the polymers, polysaccharides obtained in lemon, and which can work together with carbonate, therefore with a ceramic, therefore possibly with something that can be even obtained from eggshells, for example. And limonene carbonate is promising in terms, it's still under research, but it's promising as a new and really different bioplastics. So using waste, that's the last slide, just a few more minutes. Using waste, in principle, it is something that it's a plus sign on sustainability, because waste has to be disposed in another way. So there is, last time we discussed a lot about algal biopolymers, algae, which contain proteins and polysaccharides together, which is very interesting in terms of the properties of the bioplastics, because there has been a tradition also of bioplastics protoplastics, because remember that before the year the 30s, plastics, the first protoplastics like bakelite, which was a phenol plastics obtained from petrol. Phenol was one of the first patents that was owned by Bayer, and at the time of the aspirin, so it was at the beginning of the 20th century, and before bakelite and PVC, basically polyvinyl chloride, there were the so-called proto-plastics, so the plastic before the plastic, which were the gallolith from milk whey, the cellulose acetate, which is still between us and still used, and the Guadu seed. And they were all obtained. There were more than this, and there were a number of phytoplastics. In fact, the journal Plastics, which is coming out from the end of the 19th century, if I remember well, was dealing with this kind of protoplastics. Materials which were moldable and deformable, basically, and which suffered not obvious degradation. And they were always obtained by waste. Cellulose acetate was obtained by waste for the production of paper and the production of wine. Gallolith from the production of milk. It was made with milk whey and so on. Guadu seed from the butchery waste and waste from production of meat. You know, these wastes weren't always very pleasant in general terms. Also in terms of they were not odorless, these plastics. Like PLA is not odorless. That's the difference. We come back to the word of materials which have an odor, which have a scent, which is not the case for plastics. Plastics have no odor. That's what we also liked about petroplastic. We need to be clear about that. An important possibility is to use waste at 0 kilometer. Which kind of waste should I use? I should use the waste I produce, because this comes together with the indication from the European Commission is that the polluter pays principle. So the who pollutes has to pay for it, so as to dispose of his own waste. Why not producing bioplastics with my own waste? And if I am not producing bioplastics, I can produce plasticizers, hardeners, etc. I was talking about eggshells, but I could use as hardeners, I could use mass shells which are hydroxyapatite. For example, I can mash them, make into a powder, and use as hardeners, which are present in molding of every plastic in reality. I would get rid of transportation costs, and I would also have the advantage that I know perfectly what I am putting in my bioplastics, which sometimes it's a bit of a problem, because in some cases there has been a lot of discussion about biodegradability additives. People are concerned about additives in bioplastics. If they are produced at 0 kilometer on a small scale, but even on a bigger scale, if you consider 3D printing, I may consider putting my own waste in stereolithography, for example, not fused deposition modeling, but stereolithography, so not doing with a wire, with a filament, but doing it as like addition of layers. And I could even program my own software to be able to produce my material. But this goes beyond the subject of sustainability, but using waste, it's always a good idea provided I know what waste do I have and I am able to collect it in a suitable way. Okay, um, I complete my lecture with this slide. I will give you, as always, my slides I will put in my web page.